Okay, now I know the last example was kind of, or that example one in the book is kind of formidable because they're using a lot of subintervals and the midpoint method, which is actually a little more complicated because of the fractions involved. So what we're going to talk about though right now, and we'll use a little easier example so it's a little bit easier to follow, which is mostly what your homework will be like for this first assignment, is we're going to talk about what we talked about before. We have three different ways of determining heights of these rectangles. We could use the left end point, we could use the midpoint, which is what we just did, or we could use the right end point. Now you can see that the left end point will be an under approximation if our curve is concave down, and the right end point will be an over approximation, and the midpoint looks to be kind of the best approximation. But you need to be aware of how to do all of those. So we're going to do some examples. So these are examples over on the bottom page 265 to 266. They actually go through the three examples, but they kind of give you the sketches. They show you the sketches. And then we'll just kind of follow that work, but fill in some of the details so it's a little bit easier for you to see what's going on. But again, here's what they're talking about. This is what we call rectangular approximation method, RAM. Rectangular approximation method. And again, this is using the left endpoints. This is using the midpoints. And this is using the right endpoints of these intervals for the heights of the rectangles. Now, this is concave up, so the over and under approximations are reversed what they were when it's concave down. And you have to be aware of if it's concave up or down, which will be an over approximation and which will be an under approximation between the left endpoint and the right endpoint. You do need to be aware of that. So the concavity kind of shows you what's going on. Okay? So, like I said, the example I showed over here on the first page of notes, where it was kind of looking down like this. This was see, these are concave up and this is concave down. See, that's a little bit different. Okay, that's what I'm talking about. So we'll go through each of these so you can see. So this is called RAM, and we're going to use fewer subintervals, so it's a little bit easier to deal with. So we'll try LRAM first. So we'll take a look at this one. So this is LRAM. I think that's what they did first. Yeah. Okay. And they did some of the calculations. These are the calculations you'll see on the page 266. But let's take a look at, and we'll just go back to f of x rather than the velocity function. And let's say we've got our x squared, and we want to take a look at y equals x squared, and we want to use a left rectangular approximation on the interval from 0 to 3, and we want to use 6 subintervals. So we usually let you know how many subintervals we're talking about. So we're talking about from 0 to 3, 6 subintervals. 1, 2, 3, 4, 5, 6. So if we're going from 0 to 3 and we're dividing that up into 6 equal parts, each part will be 1/2. Okay? So the length of each of these little subintervals will be 1/2. And that's going to be the base of each of these rectangles. Now, I'm going to use the left rectangular approximation. So what I'm going to do is I'm going to let the left endpoint of my interval determine the height of my rectangle. Okay? So for this first rectangle from 0 to 1/2, the base is 1/2, and I'm going to use this left endpoint for the altitude, which would be f of 0. So actually it has no altitude, it is 0. And then for this next rectangle, this will be 1/2, so that's going to be, my left endpoint will be 1/2. So I'm going to use that. Let me put these. And we leave everything in improper fractions. It's a little bit easier to deal with it. So that's the left endpoint, so that's going to be f of 1/2 will give me the height of the second rectangle. My third rectangle, I'm going to use the left endpoint 1. So f of 1 will be the height. Now remember, the base are all these 1/2. And we do that on purpose because it makes it easier to calculate. Okay? And the next rectangle here, 1, 2, 3, 4, my fourth rectangle, I'm going to use the left endpoint of 3/2. So f of 3/2 will be the height of that rectangle. The next rectangle, my fifth rectangle will be from 2 to 2.5 or 5 halves. I'm going to use the left endpoint, so f of 2 will be the height of that rectangle. And finally, the last one will be 5 halves over here. Hope you can see that's 5 halves. F of 5 halves. And that's going to be the height of that sixth rectangle. So you can see we got 1, 2, 3, 4, 5, 6 rectangles, and the left endpoints are the heights. 0, 1 half, 1, 3 halves, 2, and 5 halves. We don't use 3 because that's a right endpoint, and we're going to use 3 left endpoints. 1, 2, 3, 4, 5, 6. Don't use 7. Only 6. We want 6 subintervals. Okay? So think about that. Make sure that makes sense. In other words, we've got 6 rectangles. The heights of these rectangles are determined by the left endpoint of each subinterval. We've got 6 subintervals. And those are my left endpoints. 0, 1 half, 1, 3 halves, 2, and 5 halves. Those are my 3 left endpoints. Now, since I have 1 half in all of these, I'll just factor that out. And then I could just, each one of these will be determined by my function, and my function tells me what the height is. That's going to be whatever x is squared. So 0 squared, 1 half squared, 1 squared, 3 halves squared, 2 squared, and 5 halves squared. So that's going to give me my heights, because I have to put those in the function. And they're all over 2 or whole numbers, so this is going to be 0 squared is 0, 1/4, 1 squared is 1, 9/4, 2 squared is 4, 5 squared is 25 over 2 squared, which is 4, so it's 25/4. And because they're all common, they all have the same denominators, all the fractions, we can divide this up, and my fractions would be 1/4 plus 9/4 plus 25/4, so that's 10 plus 35/4. 10 plus 25 is 35/4, and 1 plus 4 is 5. I got 1 half times that, and I'm doing all these, most of these without calculator to the very end. So there's lots of ways to do this. I just use the distributive property. This is 1 half of times 35/4 plus 1 half times 5. And that ended up being 35/8 plus 5 halves. And I want to add these fractions, so I put them as a common denominator of 8, so I multiply the top and bottom here by 4. And I get 20/8. So 35 plus 20 is 55/8. If I divide 8 into 55 finally, and I could have changed these to mixed numbers anywhere along the line and worked my calculations out like that. 6 times 8 is 48, and 7 left over, so 6 7/8. And finally, I'll use a calculator, and I get 6.875, which is what you see on page 266. So that's how they calculated that out. Okay, so this is what we call the LRAM, or the left rectangular approximation method. Okay, now you can see, now we actually figured this out. This is the same function, x squared, or we use t squared. We figured that out using 12 subintervals and using the midpoint, and we got 8.98. And I told you that that was actually, the actual value would be 3. We'll show you that later. Okay, so this is quite a, I'm sorry, the actual area was going to be 9, excuse me. Did I say 3? It must have been 9. I was thinking the interval was 0 and 3. The actual value is 9, and we're quite a bit under. So this is quite a bit of an underestimate. Okay, so it's probably not the best way to estimate this, because you can see this, all these little gaps here that we're not getting with our rectangles. So definitely is an underestimate. Okay, and that's mostly that's because it's concave. It's concave up. If it was concave down, this actually would be an overestimate, and we'll show you how that later. Okay, so anyway, hope that makes sense, and take a look at that and try to, you'll have to do some of these for your homework, okay? You have to do a left RAM and a right RAM and a midpoint RAM, or MRAM we call those. So take a look at that and make sure that all makes sense, and you'll have to do all this arithmetic, so be aware of that.